I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. We thank you for the weekend just completed, and I just pray that you'd guide our thoughts today, Lord. Help us to, again, just to glorify you what we do, Lord. In your name I pray. Amen. So I had a question. Do any of you have a conflict with having the test next Monday? That's not a relevant question. Yes. You have a what? Does anyone have a problem with next Wednesday then? No, it's on what it's on. All right, next Wednesday it is then. So in view of that, I will take questions about the test on next Monday. All right?
I'm just wondering if anyone actually wants to do it next Wednesday. Like, were you asking us if we ultimately wanted to do it next Wednesday? Or?
I'm not really asking. I'm asking if anybody has any conflicts next Monday or next Wednesday.
Okay. Just
yeah.
because why the change?
What?
Why are we changing?
What?
Why are we changing the schedule?
Yeah, Wednesday sounds great.
Because I'm a kind and malevolent, that's the wrong word. Benevolent leader, yes. Yes?
You said you're collecting the training problems on Monday?
That seems like it would be the most productive for you guys, yeah. Right? Yeah. So for those of you who are planning to do a third of the training exercises over the next 48 hours, first of all, that's really, really dumb. Right? That is totally the right way to do bad on the test, which was ostensibly going to be Wednesday. So don't do that. It will not always be the case that I get so busy I don't have time to construct a test for you properly by Wednesday. So no, that's not the real reason. That's not the real reason. No. This sort of thing tends to happen this part of the semester. Things get too bunched up. I get too into making a homework for another class and forget I have things to do, stuff like that. Anyway, more to the point, I do need still to post mission 6 solution before you have the test, right? So the earliest that'll be up is like tonight. So I don't think that's fair to you. I'd like you to have a little bit more time to look at that. So, yeah. Oh, okay.
I was thinking we had a mission maybe due the following week, but we don't. So
yeah, I think that. Yeah, I think I pushed I think the due date probably can even stand because I pushed it back far enough that it won't. But all right, so rings. All right, so definition. A set R is called a ring if it has an addition, let's say plus, which goes from R cross R to R again, and multiplication, which we'll say is denoted by AB maps to AB for all A comma B in R cross R, such that, and we got some ring axioms. First of all, A plus B is equal to B plus A. Ring axiom 2. Addition is associative. There exists a 0. Ring 4. For each A in R, there exists minus A in R such that A plus minus A is equal to the 0. All right? Bring axiom 5. ABC equals to ABC. In other words, multiplication is associative. Ring axiom 6. There exists 1 in R such that 1 times A is equal to A times 1 for all A in R. And then ring axiom 7 is that if we have A times B plus C, we get AB plus AC, and also B plus C times A is equal to BA plus CA. So we get left and right distributivity. That's ring axiom 7. And then finally, if in addition, and he calls this R8, Nicholson does, AB is equal to BA, then R is a commutative ring. So sometimes you might say something like R, comma, plus, comma, dot, or something like that to indicate that the ring is really, it's got a lot of structure, right? It's a set paired with two things, an addition and a multiplication. The addition has to be abelian, right? It has to be associative. There has to be a 0. There has to be additive inverses for everything. So what does that mean if you look at ring axioms 1, 2, 3, and 4?
It's a group.
Right, every ring is an abelian group with respect to the ring addition, right? However, the rest of the structure there is not quite enough to give you that it's a group with respect to multiplication. In fact, it can't be, because there's a 0 in it. Right, so unless 0 equals to 1, you're in trouble. 0 equals to 1 is a stupid ring. You don't care about it. But certain theorems have to be stated in that way. Suppose the ring is, you have a ring such that 0 is not equal to 1, and then you can say things. Now, this is the definition in Nicholson. It's at odds with the definition I used last time I taught this course. The last time I taught this course, axiom 6 was not present. Okay, so some people define a ring to be everything here except for axiom 6. And then they'll say if you have a ring and it satisfies axiom 6, then it's a ring with unity. So you got to be aware of that notation, that terminology, because a lot of people use it. Other people say horrible things like if you have R with ring axioms 1 through 5 and ring axiom 7, then R is a RNG. Because it's a ring without identity. This is standard terminology in some books. I'm not joking. But anyway, so then you're left with the question: what do you call the ring without identity? Well, the terminology that Nicholson uses is general ring. A general ring for Nicholson is a RNG. He doesn't say that. I'm just saying that. I don't know. I would say it's a ring without identity. Yeah. I like the ring of that. Let's see here. Sorry, I should stop. We should all stop. So some examples. So many examples. So many examples we've already been using, right? One, the integers, the real numbers, the rational numbers, the complex numbers, right? Zn. These are all commutative rings, right? Number two, if you let, R be a commutative ring, then you can define M, he calls it Mn of R. I would tend to call it R n by n, whatever. It's a set of n by n matrices with elements taken from the ring. Well, this also forms a ring, the so-called matrix ring over R. What's the addition? What's the multiplication in here? So 0, that's just 0 for all ij, right? That's the 0 matrix. What's my addition? What's my multiplication? If I have a plus b ij, my addition is aij plus bij, right? That's the definition of addition in the matrix ring. You just add component-wise. It's easy to check that this addition takes that 0 as a 0, and it's associative, and it's commutative, right? Why is it commutative? Because R is commutative, right? It's commutative because this is equal to bij plus aij, right? Which is b plus aij. So there you go. There's the proof, since that holds for all ij, that this addition is commutative, right? And then there's multiplication. So if I have a, b, ij, well, definition, that's the sum k equals 1 to n of a, I, k, b, k, j. It's easy enough to verify that that's closed, right? Why? Why is the thing on the right-hand side of that equality in the ring again? Since it's what? Formed by sum of products in R, right? What do the ring axioms give you? They give you a pair of binary operations, addition and multiplication, which close back in again on themselves, right? That was even up here. This is supposed to be an element of R. I forgot that, but what's that? I just missed your last word.
Before we list the axioms, we already assumed that they're mappings that are closed.
Yes. Yeah. I mean, yeah, otherwise, I think that has to be said somewhere. Otherwise, I don't know what some of these mean. But given that, it's clear that AB is, in fact, again, each ij, for any choice of ij, that this is a sum of products of ring elements, which is, again, a ring element. So it's closed. It's also, n by n. And you can easily show that the identity, right, if I want the identity matrix, well, you know how to define it. Ij is equal to the Kronecker delta ij, right? That's 1 for I equals to j, and it's 0 for I not equals to j. And for the usual reasons in linear algebra, you can show that, it's a claim. You can check that a times I is equal to a is equal to I times a, right? Of course, this is not a commutative ring, right? So matrix ring is a nice example. There are other things. A nice class of examples. Something like this. Let S be a ring. And Well, I'm not sure if I have to make it. I'm just going to make it a commutative ring just to stay out of trouble. That might not be necessary, though. Let S be a commutative ring, then let R equals to S of X. So what is this? This notation, S brackets X, is by definition A naught plus A1X plus da 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 plus ANX to the N, such that the coefficients are taken from S. And N is a natural number. So this is the so-called polynomial ring. Polynomials with coefficients in S. Yes. So since there's confusion about that, let's say, there we go. Okay, fixed. Now, so how do you add things in the polynomial ring? How do you add polynomials? So if we have A naught plus A1x plus da 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 plus AN x to the n, and we want to add that to, say, B naught plus B1x plus da 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 plus, they don't have to have the same order, do they? So say BM x to the m, right? Then without loss of generality, we can assume one of the orders is larger than the other. Which one do you want to do? What's that? M. M is bigger. M for more. M is greater than n. Okay. So then, of course, we can express the first polynomial as what? You know? Same. It's that. And so by definition, we just add components, right? A naught plus B naught plus A1 plus B1x plus dot 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 plus, you know, I mean, and so we could say that A sub n plus 1 equals to 0, and we could say that this is A sub m equals to 0 for the sake of not writing so much annoying stuff. So people who are smarter than me would say that the lazier way to denote this is something like this. F of x equals to the sum n equals 0 to infinity of a sub n x to the n, and g of x, the sum, n equals 0 to infinity of bn x to the n, where only finitely many a sub n and b sub n are non-zero. That's a convenient way to define polynomials. And that way you don't have to fuss with this maximal order thing I'm just fussing with, right? When you add them, you just add coefficients. The fact that only finitely many of them are non-zero means that when you add them together, you still have finitely many non-zero things if you just add component-wise, right? I'm actually giving you the proof that the sum of polynomials is a polynomial in that sense. And then the zero polynomial, zero coefficients all the way down, how do you multiply them? Yeah, we'll talk about that some other day, but you can, right? So, but now I'm getting too far into the weeds. We have a whole section on polynomials later. I'm really just throwing it out here as an example. We'll finish the rest of it there. But there are further, but you already know how to multiply polynomials, so I could add formalism to it. But the truth of the matter is you just multiply like normal, and you can prove that if you start with finitely many things, for each of them, when you multiply it out, you still get finitely many things according to the usual rules of polynomial multiplication. So that's another ring. If you look at, he's got this, he says like, well, he says f x comma the reals. So what's this? This is, he says real valued functions from some set x, which let's say is non-empty. How do you, does this have a ring structure? What if you add together functions? How do you add functions? Pointwise, right? Just basically the addition and even multiplication of functions all happens in the range, right? So like if you think about it, f plus g, right, of x is equal to f of x plus g of x, and f times g, not composition, but actual multiplication here, of x equals to f of x g of x. Well, these will define ring structure. On this thing. But really, does this have to be real valued? If you put a ring there, if it's, I don't even think it needs to be commutative, honestly, right? I mean, if you just put a ring there, that gives you an example. As long as it's ring valued, since the addition and multiplication happens in the range, you're good to go. You won't be surprised when I also tell you if we have R1, R2, Rn rings, then R1 cross R2 cross cross Rn is a ring. And I won't subject you to the plethora of notation I did when we did the group product, right? But technically, each ring could have a different multiplication, right? I'll be lazy and denote them all by juxtaposition here, but the multiplication is just what you'd expect. You just multiply component-wise. How do you add component-wise, right? And then you can, what would the identity be in the product ring? Right. If I call this whole thing R, then the identity for R actually works out to 1, 1, 1, 1, yeah. Where technically, if you want me to be fussy, this is the 1 for ring 1, the 1 for ring 2, the 1 for ring n. Those could all be different objects. In principle, the first one could be a function, the second one could be a matrix, the third one could be a residue mod n number 1. I mean, you could take all kinds of different ones, you know, if you want more flavor choices. Okay, enough about that. Now, he has a number of basic ring theorems in this section, which I think are not especially exciting, but I'll write them down because they are things we should know and be willing to use. If I can find a good place to, I guess we don't need, you guys know matrices where we can get rid of. Curse it. Well, fine. So here's his theorem 1. Of course, this is section 3.1. And here it is. If 0 is in the ring, is the 0 of a ring, then 0 times r is equal to 0 is equal to r times 0 for all r in the ring. You're like, well, isn't that true? Yes, but we should prove things from the axiom, right? That's kind of the point of axioms, isn't it? So here we go. Proof. Given are in the ring, what do we have? I'm going to ignore his proof and see if we can come up with our own. How about that? What do we know about R? It's distributed. So how about R plus, well, maybe that's not the right way to go. I guess notice, yeah, it's distributive is the right key. Note 0 plus 0 is what?
Or do we want to try 1 plus minus r is equal to 0? 0 plus r equals r.
Well, that's also true. 0 plus 0 is 0, right? So R times 0 is equal to what? Right? Which by the distributive axiom is R times 0 plus R times 0, but this is an additive abelian group, so we have cancellation. So this gives us that R times 0 equals to 0. And by the other kind of distributivity, we have 0 times R is equal to 0 plus 0 times R, which is 0R plus 0R, which of course by cancellation implies that 0R is equal to 0. And there you have it. So yeah, it's distributivity. I'm sure you could find a way to use other axioms to prove it and go in various circles. I know I could certain days. There is a stupid ring. I'm not making some sort of comment about marriage. Let's see here. Wait, no, marriage is good. It's good. It's good. Ring by spring. Ring by spring. So if we put 0, actually ring by October 23rd, which is rather satisfying if you look at this lecture, right? Just saying. So this is the stupid ring. So in this ring, 0 plus 0 is 0. 0 times 0 is 0. And that's kind of it. So 1 is 0 in this ring. If you sort through the axioms, they work. So we have to be wary for this as we state theorems because it's not a happy example. All right. Theorem 2 got a little bit more substance to it. And if I have any good sense, I won't try to prove it today. I don't know. I mean, we can prove one of them, I guess. I'll let you guys do it. Let R and S be arbitrary ring elements. All right. And then we have the following 1 minus R parentheses times S is equal to R times parentheses minus S is equal to minus parentheses RS. In other words, you can move the minuses around like you're used to. Minus R minus S is equal to RS. And 3, if you got integers, M and N, in the integers, then we've got MR and NS equals to all right. Now, these are like 3. Remember that this is just the exponent, quote unquote, notation for an additive group, right? That's notation for repeated addition or repeated subtraction as appropriate in the ring. That notation still holds here because a ring is an abelian group with respect to addition, so we still have the additive notation for exponentiation, right? I mean, that's still in play, that notation. He has a nice table of that on page 162. These ones. Let's see here. Sorry, that service only available until the front row. All right, so how would we prove one of these? Which one do you guys want to? Well, let's try to prove the first one. How about that? Now, should I actually look at Nicholson, or should I just try to hunt a proof down? Let's write down some things that are true. First of all, we should let R and S be ring elements, right? And notice that we do have that 1 times R is equal to R times 1, right? And likewise for S. That's one thing we know. What else do we know? Also, 1 is in the ring, right? Therefore, -1 is in the ring, and what's the deal with -1? 1 plus -1 is equal to 0. Right? So what happens if we look at R times 0 is equal to R times 1 plus -1? What does that tell us? First of all, from theorem 1, we already know that R times 0 is what? This is 0, right? And then we can distribute, right? 0 is what? 0 is equal to R times 1 plus what? R times -1. But R times 1 is also equal to R, right? So thus, 0 is equal to R plus R times -1. Right. So therefore, minus R is equal to R times -1. Which isn't what we set out to prove just yet, but it seems relevant, right? And you could also prove, likewise, if we look at 0 times R is equal to 1 plus -1, right, times R, that will tell us that, 0 is equal to 1 times R plus -1 times R, which will then tell us that 0 is equal to R plus -1 times R, which will then tell us that -1 times R is also equal to -R. That's great, but it doesn't actually help me prove this just yet, does it? Does it? If I already had 3, I could prove 1, but that'd be bad form because in the book he uses 1 and 2 to prove 3, so that would be kind of awkward. But yes, circular proofs are often easier. But yeah, I mean this is like all possible cases. These are like special cases that build to 3. Let's see here. So we have then that let's think about it then. Minus R times S is equal to what? Apparently that's, what is that? That's R times -1, right? R times -1, parentheses, times S, right? But that's actually all we need, right? because then associativity of the ring gives me that this is R times minus 1, parentheses, times S, right? By axiom what? 5, right? But then again, I mean, I did this for R, but of course this is also true for S, right? There's nothing, these soon-to-be green lemmas, both of these, both of those lemmas, they hold just as well for S as they do for R. And so what's that? Well, that's R times minus S, yeah.
And similarly, you take out the minus 1 on the left side, you get the other.
Okay, so similarly, the next equality holds, right? Yeah. And then once you know that, proving the thing below it is actually not hard, right? Because, so if to prove this, I'll do 2 in blue. But if you start with minus R times minus S, what's that equal to? This is equal to R times minus 1, right? Times minus 1 times S, right? Which is equal to R times minus 1 minus, using associativity and my lemma, that minus 1 times minus 1 is minus minus 1. But minus minus 1 is 1 again by definition of additive inverse. Because minus 1 is what? It's the number such that 1 plus minus 1 is 0 again. So this is 1.
With regards to B equals A inverse plus A inverse.
Yes. And so that's RS. Again, using the axiom. Okay, enough of this. You can look at the proofs of 2 and 3 in the book. Enough. I mean, you guys could read. The point is that these items here, just logically, you should be aware, these aren't part of the definition of a ring, right? But they come for free. Commutative or not, these are true. Even for a non-commutative ring, like a matrix ring or quaternions, these are still true. Now, there's an important idea about a ring, which is called the characteristic. The characteristic of a ring is the number of times, essentially, that you have to add the 1 and the ring together to get back to 0, if at all. So here's the definition. The characteristic of R is equal to the smallest, let's say, P, such that, maybe I shouldn't use P, we think prime, right? Smallest n, such that n times 1 is equal to 0 for the ring. And what else? You're like, well, that's crazy. My favorite examples never have that happen. What do you mean add 1 to itself so many times you get back to 0? That's nuts, right? If no such n exists, then the characteristic of the ring is infinity. No, actually it's 0. So it's called characteristic 0. So what are characteristic 0 rings? How about reals, rationals, complexes, right? Matrices over any of these, right? All of our favorite examples are characteristic. All my favorite examples are characteristic 0. Now, if you're a number theorist, maybe you like things that live in characteristic n, right? What's the characteristic of Zn? It's n, right? What's the characteristic of matrices built with these guys? Or what's the characteristic of polynomials built with these guys as coefficients? It's going to kind of a snooze fest here. It's just n. It's n. It's n. Yeah. So it's called the characteristic of a ring. He points out that the binomial theorem holds for a ring. Provided it's a commutative ring, we get a binomial theorem. Just like you know and love. And at this point, he moves on to subring tests and some further examples. I'm going to save that for tomorrow. Tomorrow, you know what I mean, Wednesday. And what I want to do is spend the remaining class time just talking about where we're going in terms of terminology. I think it's helpful to give the big picture at this point. Nicholson has the big picture kind of like sprinkled over the next few sections. I think it's helpful to stop and just try to give an account of where we're going. So the next definition we'll learn not too long from now, in fact we kind of already know it, is that U, an element of R, is a unit if what? There exists V in R such that UV is equal to 1, right? Yep.
So is this like, just like we're thinking of R as a group over addition and then a monoid over multiplication with a bit of extra structure, so unit means the same thing for multiplication.
Let's assume commutative. What's that? I'm sorry. So I think you're right. Monoid, we need what? We need, with multiplication being a monoid, we need an identity, we need associativity, and that's it. So it's a little bit more than that, right? I mean, it's...
But we can use the same definition of unit.
Yes, right. That's what I was saying, is like, I think it's not... although I'm trying to remember, our monoid didn't have to be commutative, did it? And did we have... I feel like if it's not commutative, then you need more than just this. You need... I mean, it seems like in principle, well, now I'm getting too far into the weeds at the moment. I mean, let me stop. Anyway, the point is a unit has a multiplicative inverse, okay? Let's just keep it commutative here for a second. This is going to bother me if I can't find it. Stupid thing, where'd you go? It has to be a left and a right inverse, actually. So let me just get... UV and VU equals 1, we denote. Here, I'll uncomplicate my life. U inverse is equals to V. Okay, forget the commutative even. This is a unit. All right. 0 cannot be a unit. All right? What if it was? Would contradict theorem 1. Right. Unless what? Unless it's a stupid ring, right? So 0 is not, except in this stupid case, 0 is not a unit, all right? So then there's further terminology. If every U not equals to 0 in R is a unit, then R is a division ring, right?
Is that a field or is it?
A commutative division ring is a field. That's another way of saying what? It's commutative and everything non-zero has a multiplicative inverse. usually people give the quaternions, which I usually denote like this. Quaternions, it's like a double bold H. This is things of the form T, Xi, Yj, Zk, where Ij and K are in the quaternion 8 group for us. And T, X, Y, Z are real numbers. So, sorry, anyway, the quaternions, which we'll talk more about some other day, obviously, but the quaternions are actually an example where it's a division ring, but it's not commutative. Okay, so there you can prove that every quaternion has a well-defined one of these guys, provided that this is non-zero. This actually makes sense. It can be rewritten as A plus BI plus CJ plus DK for appropriate ABCD. Yep.
Do we talk about fields in this class or just 422?
Yes, we will talk about fields, but just baby fields in here. We continue talking about fields in 422. We will start talking about fields in here. But yes, a field is a commutative division ring. Now, so ring is sort of your basic object, right? Now, there's various, we can add structure, all right? In a ring, one of the things you want to avoid, I've left myself no place to write. This is, when I give a big picture talk, I like to have some kind of reasonable thing on the board you can look at and follow. So here, let's try this again. So here's rings, all right? So inside this, there's what you might call integral domains. What's an integral domain? Right. So what's a zero divisor is really the question then, right? So definition, if A and B in a ring have AB equals to 0 for A and B not equal to 0, then A and B are called zero divisors. Okay. So an integral domain, R is integral domain if R has no zero divisors. So what's an example of an integral domain? Matrices with respect to multiplication? No, those got zero divisors.
Oh, I'm sorry, I was giving an example.
Oh, not an example. So your clue is this word right here. So like the quintessential integral domain is the integers. And of course, you're right. The real numbers, the complex numbers, the rational numbers, right? Another good example of but then below this still, we have fields. And I probably should, I probably should partition off over here in a corner. And this will offend some mathematicians, but non-commutative rings. I mean, this is exactly probably opposite the actual story, in that non-commutative rings are very complicated and unwieldy and large subject. But we spend the majority of our effort in this class and the next on commutative ring theory, because it's where things are nice. So integral domain is a commutative ring with no zero divisors. A field is smaller still, right? It's what? This picture. So every non-zero element has what? Inverse, right? Multiplicative inverse. So what would be here would be something like z mod p, right? What's that? Z mod p to the k? Oh, yeah, I'm not ready. That seems like more of Math 422 comment, but you're probably right. I mean, I'm not saying you're wrong, but I am trying to keep it easy for the moment. But you're right. So here, like z6 is not an integral domain because in z6 we have 2 times 3 is 0, and neither 2 nor 3 are 0, right? So Zn gives you an interesting example of something that's a ring but integral domain. Z isn't a good example because it's an integral domain, but is Z a field? Z is not a field because 2 is in Z, right? But 1 over 2 is not an element of Z, right? So, yep.
So in your definition there, are you saying that if you have such an A and B multiplied to 0, that we call those zero divisors? And
Yeah.
we define its integral domain if there are no such A and B?
Right. So these are. But anyway, that's enough for today. So we'll get back to it Wednesday. Thanks, guys. Sorry to deprive you. I know you really were looking forward to the test Wednesday.